The electric dipole is two charges that have the same magnitude but exact opposite values, negative q, for example, and q. And they are at some distance d from each other. When you have two opposite charges at distance d, we call it electric dipole. And we want to find along the axis of the dipole at some distance x, and let's say this is the y-axis, this is x-axis. We want to find the electric field of this dipole. Now this positive charge creates its own electric field at this point, and this negative charge creates its own electric field at this point, right? Which direction is the direction of the field of the positive charge? For positive charge, is it positive? The field is away from it, right? So this is this way. Let's say this is 1, this is 2. This will be E1. And this one creates a electric field toward it. So this is E2. And because Q, they have the same magnitude, but the positive one is closer, E1 is larger than E2, right? Because Q1 is closer. And in order to find the total electric field, you need to do E1 minus E2. The magnitudes actually can't subtract because they are in the same orientation. So the electric field in this case will be E1 minus E2 in magnitude. And E1, if this distance is x, this is an x-axis, this is y-axis, so this is point x from this point, right? So the electric field of E1 will be k q divided by this distance, which is R1, let's say. R1 is x minus d over 2. X minus d over 2 squared. That's the electric field of the first one. The other one is k q, absolute value, divided by x plus d over 2 squared. Right? This is from here to here is x. The distance here, R2, is x plus d over 2. Right? This is d over 2. This is d over 2. So this is x. So R1 is x minus d over 2. R2 is x plus d over 2. Right? So the total electric field will be like this. Does that make sense? And now we can factor in KQ, and Q will be KQ is one of the Q's, and then it will be 1 over x minus d over 2 squared minus 1 over x plus d over 2 squared. But this is the result, this general result. But usually we are interested in the cases where this distance x is much larger than the distance between the charges. For example, if you're considering molecules, molecules have a little bit of positive and negative charges separated from each other because they are polar. And then you're considering some distance away. Usually that distance is much larger than the separation of the positive and negative charges. You want to see what is the limiting case when you go far away from the dipole. So when x is much larger than d, we want to do some approximation here. So if I factor in x from each one of these and pull it out, I get an x squared in denominator here. So E will be k q over x squared. You see, if I factor in x, it gets squared and then comes out. And then what I have will be x 1 minus d over 2x, right? Get 1 minus d over 2x to the power negative 2, right? Minus the same thing, 1 minus d over 2x to the power negative 2, plus that, right? And now I want to use binomial theorem again. Remember, binomial theorem for approximations in physics is very important. Binomial theorem says if you have 1 plus x to the power n is 1 plus nx plus n times n minus 1 over 2 factorial x squared plus n times n minus 1 times n minus 2 over 3 factorial times x cubed and so forth. It's like a Taylor series. And because if x is much larger than d, this is a small factor, so we can expand it and just keep the first term because the other terms will be much smaller. So if I do that, then the electric field will be q over x squared. And for this one, I'll get 1 minus, see, x will be negative d over 2x in here, right? And n is negative 2. So it will be 1 plus 2d over 2x, 2d over 2x, or I could say negative 2 times d over 2x, and then I ignore the other terms. Minus, for this one, will be 1 plus negative 2 times d over 2x. And I ignore the other terms, because these are the leading terms. Now see, this 1 and 1 cancel each other. You have d over x here, minus d over x. We get 2d over x. And this q times d has a name. We define electric dipole moment for any dipole is the magnitude of each charge times the distance between the two charges. And we call it P. And in terms of that P, E becomes 2kP divided by x cubed. So this electric field of a dipole depends on the dipole moment and with a factor of 2k, and it drops with the cube of the distance. For a point charge, the electric field drops by square of the distance. For dipole, the electric field drops with the cube of the distance. And this is the main feature of this. Of course, this will be a bit different if you are in any other orientation from the dipole. Particularly if you are going in this direction, it will be a little bit different. In order to calculate that, let's say you have a dipole in here, negative q and q, and the distance is d between them, and you are at distance y. This is x, this is y. All right, at this point P, we want to find the net electric field for these two. So this one creates an electric field like that. toward it because it's negative. Right? This is E2. This one creates an electric field this way. It's E1. So if you want to calculate the net, you see that from symmetry, the y component cancels out. The x component becomes twice the x component of each one. So if this is the angle theta, or this is the angle theta, it will be E1 times cosine theta. So the net electric field at this point, because the y components cancel out, the x components add up, and they are the same, becomes 2 times E1 times cosine of this theta. Right? And what is E1? E1 will be, if this is R, will be KQ over R squared. And R squared is y squared plus d over 2 squared. Right? That would be KQ over y squared plus d over 2 squared. That's the magnitude E1, and then you want to multiply it by 2 by cosine theta. What is cosine theta? I want to write it in terms of y. This is y. This is d over 2, right? What is cosine theta? And that right triangle is adjacent over hypotenuse, right? So d over 2 divided by r, which is square root of y squared plus d over 2 squared. So it will be kp divided by y cubed. So this is the result when you go in this direction. That's the result when you go in this direction. They're different by a factor of 2, you see? This is kp divided by the distance cubed. We multiply by 2. This is just kp over the distance cubed. It's different. So it depends on which direction you go. Right? What happens if you put a dipole in an electric field? We have two forces acting in different directions. The net force is 0, but there is a torque. How do we calculate the torque? Who remembers torque from physics 1?
Force times distance times the sine of the angle between the two vectors.
Force times distance times the sine of the angle. For example, if this force around this, right? This is the distance that the force applied. This is the force. You multiply this distance by this force times the sine of the angle between them. Or you can say force times perpendicular distance. This will be a line of action. We say this is called line of action where the force applies. And perpendicular distance of the pivot point or axis of rotation to this line of action will be R perpendicular. We say torque R1 is F1 times R perpendicular for that. Or you can say this because this R perpendicular is actually this R times the sine of the angle that you're talking about. So it's the same thing. So let's say there is an angle between this dipole moment. Dipole moment is in this direction. The electric field is in this direction. And there's angle here. Angle theta between the electric field and the dipole moment. Dipole moment is this way, the electric field is this way. I didn't talk about the direction of dipole moment. Dipole moment is like a vector. It's from negative charge to positive charge, but that is its magnitude. Right? So if this is the angle, and that angle is the same as this angle, the same as this angle. So the torque of F1 is equal to F1 times d over 2 times sine of this angle. So tau 1 is F1 times d over 2 times sine theta. Theta is the angle between the dipole moment and the electric field. But F1 is Q times E. So tau 1 is Q times E times d over 2 times sine theta. And then what about torque of this one, F2? Tau 2 is also the magnitude of the force times that perpendicular distance, which is the same, isn't it? But are the torques in the same direction or opposite direction? Same direction. So the torque of the force F2 is also the same. So it will be Q times E, the magnitude of the force, times d over 2 times sine theta. And then if you add the two, net tau is equal to tau 1 plus tau 2, which is this plus that. You get 1/2 and 1/2 becomes the whole thing. So tau becomes E QD times sine theta. And this QD again is the magnitude of the dipole moment, right? So tau will be E times P times sine the angle between them. And the torque is in which direction? The torque, you know, you can use right-hand rule. Distance times F, right? Into the page. For this one also, R times F is into the page, so they're both into the page. And you can write it as the cross product of P and E. So P cross E, tau is P vector cross E vector. And it is a vector equation. You can always write it like that. Of course, I could be more mathematically rigorous and talk about the cross products here. You know, this R cross F and this R cross F, if you add them, will be total R cross F, and then will be total P cross E. That's their main result here. So if you have a dipole in an electric field, it feels a torque. The torque is dipole moment cross electric field. All right? And for example, if you have a polar molecule in an electric field, it tends to rotate and align itself with the electric field. And the torque is given by that. All right, any questions?